Hello and welcome back. Today I'm going to do problem 41 from section 11.9, and this problem states use the power series for tangent inverse x to prove that the following expression for pi as the sum of an infinite series. So I would recommend, if you do not know power series, please go back to 11.8 in the early transcendentals, and it will help a lot because this first step I'm not going to explain, but we're going to go through the proof and see how it works step by step. So we have pi, and this has to equal our tangent inverse, and it's of x, but we need an angle here that we're going to be plugging into our whole problem. So I'm going to choose pi over 6, and I'll explain why here in a moment, and that's going to be root 3 over 3. This is equal to the sum, n equals 0, and this is inverse, so alternating series here, n multiplied by x to the 2n plus 1 all over 2n plus 1. Like I said, this wouldn't make sense if you don't know power series, so please go back to that section. But moving on, everywhere we see an x, we're going to plug in what we're using for x, which is root 3 over 3. Now, why did I choose root 3 over 3? Specifically because I know that 6 here on pi over 6 is going to be pulled out as a constant, so he's going to go right in front of our sum. And I know root 3, the only way to get a root 3 is by plugging in a root 3. So I'll explain as we go through. So let's go ahead and plug in what we know. So I'm going to go ahead and put my 6 out front, so multiplying this 6, so 6. I have my sum as infinity, n equaling 0. We have alternating series, which this is a constant. And then for x, go ahead and plug in our root 3 over 3 to the 2n plus 1 all over 2n plus 1. Okay, organizing our work, we're going to work with this top portion here. So this looks like root 3 over 3 to the 2n plus 1. I'll add in the denominator once we get this simplified as much as possible. So we're going to split this. So what that's going to look like is I have essentially a root 3 to the 2n. So we have root 3 to a 2n, and then also multiplied by another root 3, and this is the plus 1. So that is how I split that. We're going to divide off and our 3 to the 2n plus 1. All right, now at this point we can go ahead and add in our original denominator. So big line, we're going to go 2n plus 1. Okay, simplifying this a little further, we are given 3 to the squared. This is going to cancel with this, so we can say this is just 3 to the n multiplied by the root of 3. This is all divided by, let's get a new sheet here. Okay, so where we're at is we have 6 sum n equaling 0 alternating, and then at this point we were at the root 3 to the 2n times a root 3. We're going to divide that all off by 3 to the 2n plus 1, and that came from our initial numerator divided by our original denominator, 2n plus 1. All right, one step further, here we're going to split this off, so I know the square root of 3 to the 2 will cancel. So this will just get me a 3n multiplied by the root of 3 all over 3 to the 2n plus 1, 2n plus 1. I'm going to put tick marks to represent my denominator. Going one more time, we're going to say this is the same thing as 3 to the negative n. So we have now root 3 all over 3 to the negative n multiplied by 3 to the 2n plus 1. And this is still all over our denominator. So now I have a negative 1n and a 2n here. Those can just be added since we are multiplying. So let's write what we're left with. We have our sum, our constant, and now we have a root 3 in the numerator And then 1, this will give us just a 3n plus 1. So 3, and that's n plus 1. And then from this point, we have to put it all over our 2n plus 1. All right, we can still work with this denominator right here. So what this is going to turn to is a root 3 all over 3 to the n times 3. So we're splitting these per term. And then this is all over our same denominator. So once I see this portion, we are actually done simplifying, but we can rewrite it in a better way. So I noticed that this right here is a constant. So let's rewrite. We have 6 sum as n goes to 0. I have my alternating series. I'm left with a 1. So I'm not going to write the 1, but it's all over. We're left with a 3n. So the 1 was on the top. We'll just put it 1, 3n. And then our original denominator. So that's still multiplying by 2n plus 1. I'm going to put parentheses around it so we do not forget to plug it in, which we're not actually going to, but for the sake of the problem. And then I have to pull out my root 3 over 3, which I'm going to do right here. So we're going to pull that out. So this is actually multiplied by the root 3 over 3. That looks terrible. I apologize. So for our final answer, we're given 6 times root 3 all over 3. Let's just go ahead and simplify that. That means we have 2 root 3 sum as n equals 0. We are left with our alternating series still of n times 1. And then we have a 3n times a 2n plus 1. All right, if we look back to what this problem was actually asking, this matches perfectly. So we know that pi over 6 with the root 3 over 3 is actually a solution. So we just proved that this angle does work. I hope that makes sense. If you do have questions, please leave a comment. I will answer it to the best of my abilities. And until next time.